All right, so projectile motion, right? We just did the cool pearls of water demo, one of my favorite demos that I do all year. We saw that when something is launched, when it's in projectile motion, whether it is launched horizontally from some height, or if it's launched at an angle and it follows an arc, right? The horizontal motion, right? The horizontal velocity is the same throughout, right? So every speck that we saw, and every dot, that is essentially a time period, right? That is a small time period, and they're all exactly the same, right? When we do some of those pictures, some of those problems where every picture, every ball was 1 second, right? That's exactly what those were. If the water was in the air for 1 second, there would be 80 dots because it was cycling at 80. It was pushing down at 80 hertz. So there would be 80 dots as they go across, and they'd all be an 80th of a second apart. Okay, so they were exactly the exact same, distance or time period apart. And we saw that they had the same time. They were also the same distance apart. So because they had the same time and they were the same distance, they had to be traveling horizontally at the same speed, right? And the same thing happened, or a different thing happened in the vertical. And vertically, still the same time period apart, but we saw that when it went horizontally, they went from really close together, right? And as it fell, it got farther and farther and farther apart, right? And it got more curved as well, okay? So if it's going from very close together vertically to farther apart in every identical time period, then that means that it has to be speeding up, right? Follow me? And if it's speeding up, it's got to be going at gravity, because gravity is the only thing acting on the ball, or I should say on the water at that point. Okay? So that's where we come up with this idea of it's constant velocity horizontal motion and gravity accelerated vertical motion. And everything then works off of that. Okay? Follow me? Make sense? All right. So what we can do from there is we can look at our kinematic equations. And our kinematic equations actually become a little bit nicer, a little bit easier for us now. They don't change. They're still the 3 kinematic equations. Really, in essence, if we're looking at x and y, there are actually 6 of them, right? But all we're doing is changing the x's to y's, and we're changing the a's to g's. But again, especially in the x direction, they become easier, right? They actually become very simplified, and the math will further support what we saw. All right. So if we take the first one, we saw that v sub fx is going to be v sub ox plus at, right? That's our first kinematic equation. It's just the acceleration equation. Well, you saw that, and you told me that they had in the x direction, it had constant velocity everywhere, right? So this is 0. So really, it's just telling us that the final x speed is equal to the beginning x speed, right? So the math, again, is telling us what we saw, that the speed the whole way through is equal to 0, is the same from start to finish, right? It's constant. Okay? Our next one, number 2, was x sub o plus v sub o xt plus 1/2 at squared. Well, that goes away as well. So we're just left with this bit here. Okay? Which kind of makes sense. The distance that you travel is equal to wherever you started plus, right, that velocity times time. Your starting velocity times time, which again is just v equals d over t. Rearrange it a little bit. Okay? So again, pretty darn simple. In the second one, v sub f squared minus v sub o squared equals 2ad. Well, that goes away again. And you're left with then again v sub f squared equals v sub o squared. Again, telling us that the speed that you finish with is equal to the speed that you start with horizontally. Okay? This becomes useful when trying to solve problems or understanding or answering questions about projectile motion, because this allows you to, if you know the horizontal speed and you know the time, you can find out how far horizontally the object travels, right? Or you can use some of that information to answer questions later on. Okay? If we look at the y, right? Oops. This one doesn't change too much, right? So it's just v sub o y plus gt. This is just telling us that obviously it's speeding up, right? Because this is causing it to speed up as the droplet falls, right? And you've got y equals y sub o plus v sub o y t plus 1/2 g t squared, and v sub f y squared minus v sub o y squared equals 2gd, I'm sorry. So these don't really change, but again, they further support, again, what we already saw, that the object is speeding up, right? The droplet, the ball, whatever is in projectile motion is speeding up as it travels. Follow me? Good? Excellent. Give you a second. You guys are writing this stuff down. Okay. Very good? Good? All right. So let's see if I can draw this. This may not go well. No, this is not going to work the way I want it to. So we'll just do it this way. So let's say we take a ball, right? Or let's say I like this one better. We've got a cannon. And we shoot a cannonball and it goes. And over on this side is some bright, shining AP student who decides they'd want to catch the cannonball. Okay? So for right now, right, they're at the same level. Okay? So right here would be the peak with which the ball is going to be traveling. So refresh my memory. What is v sub y equal to at the top? 0. All right. How about v sub x? V sub x right there. V sub ox, right? So the x speed right here is equal to the x speed right there. Does that make sense? Devin, good? Good? All right. This is really, really helpful to remember this. Okay? If you go back to like that v sub f squared minus v sub o squared equals 2gd, well, right there, if you took halfway, there's your zeros, right? That 0, that could be your initial, and you can use that information to maybe find out how high up in the air the thing is. Okay? You could use it other places like right here to find out the time that it's been in the air. Because if you remember, if you know the height, you can find the time, right? Simply v equals gt, or that v sub o gt, right? Because what ends up being very nice is what you saw in the pearls of water was that these are mirror images of each other, right? These are mirror images. So if you know the time it takes to get here, well, the total time is then just double, right? So one of the tricks is find when the speed, if you know the velocity when it's 0 in the y direction, that can help you find the time. Okay? Once you find the time, the problem is any problem is really easy because if you think about it, X and Y are independent. They don't mix, right? Gasoline and fire. Doesn't work, right? But time is the bridge that keeps the two of them together. Okay? So time is the bridge. So if you can find that bridge, you can use X and Y equations to work together. Okay? A lot of this stuff when we work with it is just tricks of knowing like, all right, the speed up here is the Y speed is 0. Right? The X speed is the same everywhere. If I know 1/2, I know everything. Right? If I know information about half of the distance, I know the entire distance. Right? If I know the final height, or if I know the height anywhere, I can find the time at any of those points. Okay? So it's just little tricks like that that allow you to answer these questions, right? Okay. So let's look. Here we've got our cannonball. Oops. Our cannonball turned from purple to green. All right. Albert, do you want to play catch with cannonballs?
No.
That would be a good choice. So there's our cannonball, right? And then 1 second later, maybe it's right there. 2 seconds later, it's right here. 3 seconds right there. 4 seconds right here. Okay? Let's draw our vectors. If we're talking horizontally, we might have v sub x like this. And like that. And like this. Boom and boom. To the best of my ability, they're all the same, correct? They're all exactly the same. In the y direction, where is the vertical velocity going to be the greatest? At what point? Where is the vertical velocity going to be the greatest?
At the very beginning?
At the very beginning, right? Right here is going to be the greatest. Because what happens as it goes up?
It slows down.
It decreases speed, it slows down, right? So here, that might be your vertical speed. And then this is your vertical speed. And then this is your vertical. And then a little bit less. And then a little bit less. And then there would be 0 right there. Right? Okay? Because again, gravity is acting on it vertically. There's no forces, there's nothing pushing it horizontally. When could you have a change in speed horizontally? Hit something? Wind? Yeah. Or something, maybe, yeah, maybe Corey flies by on a rocket pack and flies into it and screws up the entire experiment because we're trying to get, trying to get Alyssa to catch the cannonball. We have everything perfectly done and Corey screws it all up by flying by in his jetpack. All right? So don't do that, Corey. So now, what should coming down look like?
It should be the same.
Exactly the same, right? Exactly the same. So, my poor art skills will see if we can get that to happen. Something like that, kind of close. I'm not the best at this, right? You will notice that this is my standard person whenever an experiment occurs, right? This is my standard person, right? So let's look again. Vertical velocities, they should be what? I'm sorry, horizontal velocities should be what? The same, right? So let's try and draw them exactly the same. Same, the same, the same. Okay? Horizontally, though, how should they look horizontally?
You're like mirrored images going down.
Mirror images, so reflected vertically?
Yeah.
Right? So, however long this one is right here, it should be the same but going down. Right? A little bit longer. A little bit longer. A little bit longer. A little bit longer, like that. Okay. So here's something that's interesting, and this is a good question that you might see sometimes. Let's say, that was only that's what, 3 feet off the ground, something like that, when we shot it. Okay. What if we threw something off of the Empire State Building? You can see that the longer it falls, the greater the velocity, the vertical velocity becomes, right? So it starts out kind of horizontal and it goes down, and the longer it falls for, the more vertical it becomes. will it ever end up straight down? Why not, Andy? How come the ball will never, whatever the thing is, we threw pennies off, right? How come it never ends up being straight down? Constant velocity, where? Right, so it has a constant velocity horizontal. So there's always going to be that horizontal component acting on it. Okay? And it's not changing. You can't minimize it, you can't increase it. Well, unless, wind or Corey. But what happens is the effect of it isn't changed, but it is almost lessened because the vertical becomes so much stronger, right? It becomes so much more prominent than the horizontal, but it's still always there, right? So if we looked at our vectors, right, it looks kind of, like this, like that. Right, oops, I'm going the wrong way for that one. Our actual vectors, like this, here, until you get that, and then it's right, the actual vector of the actual velocity vector of the ball. While it does become more vertical, there's still always that little horizontal piece to it. Okay, so that's also another important thing. Okay, what do you think? Does that make sense? Okay, you good? All right.